height of these two is 2, correct? So let's change that slightly. Let's make this, suppose this were your input tree.
Sir?
Tell me.
So are we allowed to insert things only at the leaves, or can we also insert them in the middle?
So, give me 1 second. So, observe that the insertions, when you do an insertion, you will search for a node, correct? And you will only do an insertion if the node is not found.
Yeah.
So you would end up at some leaf if the node is not found. At an intermediate node, you would never stop at an intermediate node, correct?
Okay, sir. Yeah.
Meaning, no, I'm lying there. For example, so at least not at a leaf, but you would have to attach a leaf.
Yeah, yes, sir. Yeah.
Meaning, it is if you are attaching your 5 here and you want to, there is a 6 here and you would want to insert 4, then you would just do it at this node. It's not a leaf, I admit, but it has one pointer which is so you will just attach a leaf node. So I should not say you should attach to a leaf, but a leaf node is what you need to attach, correct?
Yes, sir.
Okay. So, so in this tree, you see that the slope. What is slope? Slope is the difference in slope of a node V is equal to the height of V left minus height of V right. Correct? So you have a node V, it has two children, VL and VR, which alternatively we will denote by L and R, where V is understood. But their difference is called the height, is called the slope. Correct? Slope of that node. Correct? And height balance means that slope of V is less than equal to 1 for all the tree. Correct? So when you add a node here, for example, if you add a node here, this will become 1, this will become 2, 3, 4, 5, and 6. So now you can see that at 6, so firstly, what is the lowest tree that is imbalanced? This one. Lowest imbalance. This is 4. It has 2 children, one of height 3, one of height 1. So it's imbalanced. Correct? And now we will show how to correct this imbalance, where the imbalance is by at most 1 in a node. So notice that when you do an insertion, it's only along one path that heights will be affected. So after an insertion or deletion, the nodes affected, the bad nodes, the imbalanced nodes, let's say, meaning that is slope of V such that slope of V is belongs to plus minus 2. It cannot be more than 2, correct? That is, you can convince yourself to that. Slope V is plus minus 2. Such nodes form a path. The same path along which you search to find the node to insert or delete. Correct? So deletion, it will be slightly more complicated, but let's do it for one path. Correct? This balancing. Okay? Are you with me? Any questions so far?
Sir, can you repeat the last part? I didn't quite get it.
So last part means what I tell me which part? After insertion or deletion, the imbalanced nodes form a path. the path along which you went down the tree to find the
Okay, yes, sir. Yes, sir. And also, like, so, like, what have you written before slope in the last line?
that is IE.
Yes, sir. Yes, sir. Thank you, sir.
No, not that is, sorry. For all V, slope of V belongs to plus minus 2. Not that is, sorry.
So I didn't understand this. So this is in relation to what type of tree? Can the slope only be plus minus 2?
So if you take a balanced binary search tree, a height balanced binary search tree, correct? And do an insertion or deletion, then you will get only imbalanced nodes along one path.
Okay, so it's okay.
Correct? So let's think of the insertion part first and think of more complicated later. Correct? If that was inserted is present, will there be imbalance created? Every other subtree is untouched. Correct?
Sir, will all the imbalanced nodes fall on a single path?
Yes. In insertion, yes.
Okay, sir. Okay, yeah.
Because only their heights have changed, and yeah, their so a node will be imbalanced if his children's height are different by more than one. Correct? So all such nodes will lie on this tree. Correct? Lie on this path.
Okay, sir.
Correct? So now we will do a bottom-up fixing of this. Correct? So we will show how to take a node which is V, and let me, instead of VL and VR, let me just write L and R. Correct? And suppose the height of this is some H plus 2 for L and H for R. Correct? So this is an imbalanced node. We will fix that at V, the height, and then look at V's parent. Sorry. Then we would look at V's parent. Correct? So its height might also be wrong, and we will fix that successively and so on till the root. So in log n steps, we will be done, and each step takes constantly much time. You will have to shift constantly many pointers. Correct? This height is H plus 2, this height is H. The other case could be you have V, and this is H plus, this is H, and the other one is H plus 2. And they are symmetric cases. So I will deal with this case. Okay? So here the assumption I make is that L and R are balanced. I've already balanced, one of them was already balanced and the other one I've already balanced. So the first node, so in this subtree, the only imbalanced node is V. And now we try to fix that. Do you get my point?
Yes, sir.
Okay, so how do we do that? Well, height of L is H plus 2. Let's expand this by one more. So this is our L. It has two children. Let's call them LL and LR. Correct? And this one is just R. So I'm correct. So now there are some cases. So I will mark the slope. So slope of this is equal to 2 plus 2. this. So the height of this is h plus 2. Height of this is h, therefore slope is 2. What is the height of this? It is h plus 1. So what is the height of this? Is either h or h plus 1. And the height of this is either h or h plus 1. But there must be at least one h plus 1 amongst these. Correct? Do you see my point? Stop,
Yes, sir.
please stop me if you don't see anything. If anybody is confused, please stop me and I will repeat this. So I'm just saying the height of this, the length of the height of the highest, this thing is h plus 2, we said, correct? So this could be here or here. If it's here, then this one is, so that these two cases that you have V, L, LL, LR, and R. This is H plus 2. This is H plus 1. And now because the tree is balanced, this will be either H or H plus 1. Correct? Or the other cases, you have V, L, R. This is H, of course. This is H plus 2, of course. And now this LL is H, and this is H plus 1. Correct? LR is. Do people see this? That these are the two cases possible. Three cases actually. H plus 1 with H or H plus 1 and H with H plus 1. In the case HH does not arise because the height of L is H plus 2. Okay. So let's deal with this case first. It is easier. So the height of this is H. Each of these, so okay. So now what we want to do is somehow increase the height of the right side and decrease the height of the left side. Correct? I mean, the left, it is left heavy. We want to make left lighter at the expense of right. So how do we do this? This is via this operation called rotation, in which we take this V, we make its
Your screen isn't visible.
tell me.
Your screen isn't visible.
Oh, when did it become invisible?
Just now.
Just now.
Is it for everyone?
Yes, I think it is. 1 second.
Yes, sir, it's not visible for me either.
1 second. I don't know why that happened. Let's restart it. Now is it visible?
Yes.
Huh. So we will do this right rotation, in which we basically take this V and we so we take the node which was
Sir?
L. Tell me.
Sir, how can you have the case H plus 1, H plus 1? Because like
Why?
we added one node, no? And so if we,
Yes, but it could have been H and H plus 1, and you added one node on the H side.
yeah,
You could add
no,
it
but
on the
if it was H and H plus 1, then the L had H plus 2, right? Already. But we are assuming that.
No,
the
sorry. Tell me the case again. V. Give me this thing of each of them.
Yeah, so LL and LR both were H plus 1.
Both were H plus 1. I see. So this can occur while re-emerging from the recursion. By
No,
that I
okay,
mean,
sorry. The original tree had h plus 1 and h, and then we added a node to the h side.
yes, and then we rebalanced. So hold on to this thought that you have, and we will come back to it later. Remind me about it, correct?
Okay, sir.
Suppose it is h plus 1 and h or h plus 1, correct? Then what would we do? You see my point, now? So suppose it is h plus 1 and h or h plus 1, then what would we do? So,
Sir.
tell me.
So no, is L's height h plus 2 before we insert or after we insert? I'm confused.
So at some point in the algorithm, it is h plus 2. So what we will do is, if you are given such a graph, you will ensure that V becomes balanced. Its slope becomes less than equal to plus minus 1, bounded by at most 1, correct?
So like we don't, like we're just trying to balance any tree, not like when we insert or delete or something.
So we will see how to use this primitive, correct?
Okay.
Okay, so right now we have a tree in which one node is, we are considering a node which is imbalanced, the subtrees below it are balanced, and let's see how to balance it, correct?
Yes, sir.
And then we will use this routine elsewhere, correct? Are you
Yes,
with
sir.
me?
Yes.
Okay. Okay, so in this rotation process, what happens is that L goes to the top, sorry. L goes to the top. L has now R. No, sorry. Below L comes V. V still has one child R, and the other child of V is LR. So I should have maybe given them some name. But what we do you see my point? So firstly, I claim that this is a valid search tree. See that every node has respects this primitive, that all values on the left side are lesser than the value at R and is lesser than all the values on the right side. So let's check that. V to R, this was also present previously. So this one is fine. Correct? V to LR, LR was on the left side of V. So this is also fine. Do people see this? The values. So if there's confusion, stop me. Please tell me. Okay, no confusion. So V has a left child. New left child of V is LR, and LR was on the left subtree of V. So these are all smaller than V. Similarly, L has V on the right, and L was smaller than V because it was on left of V earlier, and therefore V is greater than L. Therefore, we have put it on the right side. And LR is greater than L, R is greater than L. So all these things hold. So all these four things are correct. Correct? And now let us look at the tree heights. So this was H. What was H's? What was LR's height? H or H plus 1. What was LL's height? H plus 1. And what was, so now what is the height of, so what is the height of V? New height of V? It is h plus 2, and this is h plus 3. And now the slope.
So it's h plus 1 or h plus 2, right? Height
Why
of V.
Height of V is maximum of h plus 1 and h plus 2. Sorry. That's correct. That's correct. That's correct. Sorry. So h plus 1 or h plus 2? Or h plus 2. And now this height is h plus 2 or h plus 3. Correct? Do you agree with me?
Yes, sir.
Now notice that the height of V has gone up. Height of the node at the top of the subtree has gone up. Correct? Do you agree? Might have gone up. Previously it was h plus. No, it has remained the same. Sorry. Okay, fine. So it has not gone up. It could have gone down. Correct? Fine. So the tree is now balanced because the difference in slope of this is. So what is the slope of LL has not changed. Slope of LR has not changed. Slope of R has not changed. Slope of V belongs to either 0 or minus 1 or plus 1. Sorry, plus 1. Correct? Slope of LL is whatever it was. Slope of L, this is now slope of L is belongs to 0 and minus 1. Correct? Are you with me?
Yes.
Okay. So now we have restored this invariant here. Now let's the slope of every node in this subtree is bounded by 1. Correct? Now so now we come back to the question that somebody raised, that how could this be h plus 1 and this also be h plus 1, correct? So now can anybody answer when will this occur? See, if we had a parent P and P right, and that was a left child or whatever, some child, the other child had height which was it was h plus 4, suppose, correct? And the new height of the subtree here became h plus 2. Is this a is it a case that occurs? Yeah, and this has P R R L P R R, and this both had height h plus 3. Now this is the case that was occurring, correct? Here, this is like saying two siblings were of the same height, and that was on the heavier side. Do you see my point?
Sir, could you repeat what you said?
So the question that was asked some minutes ago was that how is possible that LL has height h plus 1 and LR as height h plus 1, because we are coming up the tree, and while coming up the tree, if we do this along, I mean, how can it be possible that on the heavier side we have two equal things?
So why is that a problem? I can't see why.
No, that's not a problem. We are still resolving it, but the question was, if I understand correctly, how can the slope of some node be plus 2 or minus 2 with the grandchildren on the heavier side being of equal height? Correct?
Yes,
Okay.
sir.
But in this case, for when we do this balancing, after the balancing, it happens that this one is the lighter node with height, new height goes to h plus 2. And now, so if it was a rhetorical question telling me that it's not necessarily the, it's not necessarily along the path that we do, that's correct in some sense, but I mean, the imbalance is still occurring only along the path. So the person who asked me the question, is it clear now? Am I making sense or not?
So my question is why are we, oh, sorry. So I still have a doubt here. Why are we considering this as a separate case?
Which one?
Like when the grandchildren of the heavier side have equal height.
We are not considering it as a separate case. This is just a justification to show. So the person who asked this question before you said that we could just think of this as which one? As h. H plus 1 would, sorry. We could just think of this as one of them. I mean, this as h. Both of them cannot be equal. Correct?
Yeah.
But that is not the case. We still need to consider the case when both of them are equal, like as exemplified by this case, when these two are equal, and yet this P is unbalanced.
Okay.
So yeah, okay. So so now we have to talk about this case. One case we have talked about. And you needed, so having answered that question, I can just erase this P and everything. It will just cause confusion. Should have done this in a different. So now in this case, what do we do? So previously we rotated at V, we right rotated at V. But now if we do this, what will happen? If we naively right rotate at V, what is going to happen? Tell me. We have L, R, V, R, LR, and LL, correct? The same thing as before, what I've written, but the heights are now H. This is H plus 2. This is, this was H. So this is H still. This is, so there is already an imbalance, correct? You've increased the imbalance. Is that true? Now there is an imbalance of 3 here. So the solution is, the point is, you want to reduce the imbalance between heights. This, even though this L is balanced, this one is heavier. So if we right rotate it, this one, this LR would go deeper and it would become like this, correct? So it would cause more imbalance. So first we reduce our problem to the previous case, correct? To this case, from here to here. And how do we do that? We take the L, we basically left rotate along this. And for that, we need to mark the
Sir, what is the height of LR? Is it h plus 1 or h plus 2?
plus 1. Here, see, LR was h plus 1. Okay? The height of this was h plus 2, of L was h plus 2.
Okay.
So 2 more than R. And this is achieved via the distinctly heavier node than L and LR is H1. Correct? So what we do instead is first we draw, we want to left rotate this. So we have to expand on this node, correct? So how do we do that? We write this VL, LL, LR, and LRR, LRL, correct? Now let's mark the heights of these. So LR's height was, what was LR's height? H plus 1, correct? So now this is, the height of this is at least 1 less than that, and maybe 2 less than that. So it is H minus 1 or H, and this is also H minus 1 or H, correct? And one of them must be H. Do you agree?
So where did we left rotate
We
around?
have not yet left rotated. We have not yet left rotated. We have just written this by expanding the LR into a subtree. So we have marked the 2 children of LR as LRL and LRR.
Yes, sir.
Correct? And mark their heights. Now we will left rotate. Okay. Because for left rotation, if you cannot left rotate in this diagram only. You need LRL to go somewhere, correct?
Yes.
So how will this tree look like? V will remain the same, R will remain the same. LR would come here, and L would go here, and LL would go here, and now LRL would come here, and LRR would come here, correct? So now let us mark this again, H minus 1 or H, H minus 1 or H, H. So this must be H plus 1, and now this, notice, is H plus 2, and this might well be imbalanced, correct? And certainly this is H, this is imbalanced, V is imbalanced, correct? So, but now we are in the regime where we were earlier, meaning the children, so so are we in the same regime as before? So what we are going to do from here is to go to, so we are not necessarily in the same regime, but we would still right rotate this at this point and go to LR with R here, LR with V here and R here, and on the V we attach LR, we attach LRR, this one, and the rest is L, LL, LRL. Now let us mark the heights again. So this is H, LRL is H minus 1 or H. This is L is balanced, it is H plus 1. LRR is H minus 1 or H, and R is H. So this is also balanced, H plus 1. And now both are H plus 1, correct? And this is H plus 2. Do you see my point?
Yes, sir.
So we have done two rotations, one a left rotation and then a right rotation, correct? So, and it is easy to verify that this remains a binary search tree, correct? Each rotation preserves the binary search property, whether it's a left rotation or a right rotation. You can prove that. And then you just have to prove that the heights are appropriate. The slopes are bounded by 1 in absolute. And in this case, slopes and they are bounded by 2. Shows that. Questions? Tell me. Please don't hesitate. Ask me one, then tell me. No questions? Okay, fine. So now you might ask me, how would you compute the height of a node? We saw in the so in order to do this balancing, you need to know the heights of nodes, correct? So how would you compute the height of the node at any point of time? Tell me, anyone?
So we can recurse. Our base case will be that if it's a leaf, the height is, I don't remember the convention, either 1 or 0, and anything else we just take max of the 2 children plus 1.
Correct. So you can do this from scratch at every step. But do you need to compute the height of every node at every step, or can you maintain the heights? By maintaining the heights, I mean, when you do an insertion, for example, without any balancing or anything, just do an insertion, then the heights along that path change, correct? You see, only along this path are the heights changing. And when you do a deletion, it is similar. You can check that. Correct? So now you know the heights of each node. You have stored it in the node and you know the height of each node after this insertion. Now you do the balancing. And in the balancing, you would just use the stored heights and update them appropriately. There would be a plus minus 1 or 2 at most in the heights, And you know, if you do a right rotation, then how to update the heights. When you do a left rotation, how to update the heights. Correct? Are you with me?
Yes, sir.
So you don't explicitly have to compute the heights. You just need to maintain the heights. And all these operations take constant time per rotation. The number of rotations is logarithmic. It's proportional to the height of the tree previously. And so you can do all these operations in log n time, and you can maintain a height balanced tree in which every operation is in log n time. Correct? So that is the beauty of this method, that all these operations, inserts, deletes, searches, are all in log n time. Correct? It's like crystallized binary search. There are other ways of also doing such logarithmic height, logarithmic time operations, which we will not see in this course, or some of the assignments might indicate something about it. I'm not sure as yet. So this particular way of maintaining tree, this is a particular data structure which are called AVL trees. Trees, and it is two people, Adelson Belsky, there's one guy, and Landis. Okay, so these are called AVL trees, and these are classic data structures in computer science. You can find, insert, delete all in log n time. So if you were to do, if you were to just try to maintain a binary sorted array, then one of the insertions or deletions would take order n time. If you maintain an array rather than a list, then they would take order n time to shift the elements, correct? And insert an element in between, or to delete an element, and so on. So this is a really nice data structure, correct? So that is what I had about this one. And yeah, so now I'm just thinking. Yeah, so I heard in the assignment there were some questions about running time and so on. Not in the assignment, in the tutorial. So are people still not clear about running time and so on? I did not explicitly talk about it, but so let me clarify some things. So how do we measure running time? So the notion of complexity is what time complexity is what I'm going to talk about. So you fix some primitives such as arithmetic operations, comparisons, branches, if then else, correct? Which you say run in order one time. You also have to do, if you are using arrays, then array indexing and so on, correct? So it depends on your model of this thing. So these are order one time operations, and you want to know the time for an algorithm. So you want to say if so all your algorithms are made up of arithmetic operations, comparisons, branches, and loops, correct? So the number of times the loop runs will determine what running time of your algorithm and the number of loops and so on, correct? So if you have for I is equal to, for I in range 1, n, 0, n, do something. For j in range 0, n, do something else, and then you have some statement, some if something, correct? So if there are two loops, then as a rough, this thing, this block, if it doesn't contain any loop or recursion or anything, then it will take order one time. And there are two loops. Each loop takes order n time. So overall, it will take at most n squared time, n squared operations. And here we have tacitly specified this order notation. Order n squared. What does order n mean? Order n means that, or order n squared, what does this mean? What does order of f of n mean? So we say that Gn belongs to order f of n if Gn is less than, there exists a constant c such that Gn is less than c times fn for all n greater than equal to n naught. There exists c and there exists n naught. Gn is less than c times fn for all n greater than equal to, is eventually less than c times fn, correct? Assuming that fn and gn are all positive, this is a valid definition. Otherwise, you'll have to add a constant in the beginning and so on. So is this clear? So when we say that something runs order n squared time, means that, essentially means that it takes c times n squared time at most. There exists c, the algo runs in less than equal to c times n squared time. Am I making sense?
Yes, sir.
So that is something that is important. The running time is important. For example, of course, if you want to sort a list, the simplest way to sort a list is to, so what is the simplest way you can think of sorting a list? I mean, just you take the first element, keep it in the beginning, take the second element, see whether it is smaller or larger, keep it to the left or right, take the third element, go through the list and insert it wherever it is, this thing. So some argument, this thing you can come up with. Like if you're shuffling cards, that's how you would do, how you would sort them, correct? So next time, what we are going to see are some sorting algorithms which are better than this naive way of doing things. And we will see some naive algorithms also, like insertion sort and selection sort and so on. Not selection sort, what is it called? Insertion and what is the other one which runs in order n squared time?
Bubble sort.
Hmm?
N log.
Sorry?
No, bubble sort in n log.
Bubble sort, of course, but anyway, we'll see that next time. I always forget the names of these things. But the crucial ones that we are,
Selection sort.
is it called selection sort?
Selection
Where,
sort.
so whatever. So let's not get into nomenclature right now. The crucial ones that we are going to see are merge sort and quick sort. Correct? And both of these run in order n log n time. Correct? And n log n time is optimal for comparison based sorting algorithms. You cannot have an algorithm that runs asymptotically, meaning you can improve it only up to the constant that goes here in the order O, which is hidden in the order big O notation. But apart from that, you cannot improve on these algorithms. So
Quick sort, like if the list is sorted, it would be n squared. So randomizing makes it n log n, right? Because that's the average result for quick sort.
okay, so quick sort can be made in order n time. In random time is certainly n log n. But, you can also make it deterministic if you use so order statistic. This if you use the linear time median find, then you can do it in order n log n time. And that's a very nice algorithm which I will not cover in this course. Yeah, so you were saying something, sorry, tell me.
No, sir. Yeah.
Sir, sir, can we prove that
Tell me.
there cannot be no algorithms that work? That
Yes.
works in linear time.
That was using in which model of computation. So you can you are allowed to compare two numbers or two objects. You can just say whether one object is smaller, one object is bigger. This you can do in unit time, and you count the running time of your algorithm is the number of comparisons you make. Then you can show that you will require at least n log n comparisons to sort an algorithm, to sort n objects. Correct? Now, is that clear?
So, yeah, not completely, but yeah.
The proof is not very hard for comparison-based things. The proof just depends on the fact that there are n factorial permutations possible of n distinct objects, correct? This is clear?
Yes, sir.
So, at every step of the algorithm, you would partition the, so your input can be in any one of these n factorial equivalence classes. Meaning you have where the least object is O pi 1 and the second object is O pi 2 and so on, O pi n, where pi is some permutation. Right? So there are n factorial such permutation, there are n factorial equivalence classes. Now, if you make a comparison between this thing, if you compare OI is less than OJ, you test this, correct? Then you partition your n factorial things in at most two different classes. Correct? The permutations you partition into two different classes. One permutation in which OI is less than OJ, and the other one in which OJ is less than OI. Correct?
Okay.
So basically, you have a tree. I mean, this is not a very precise proof, but the idea is that you have a tree in which the leaves are these permutations, and you want to know. So, correct? So you have a binary tree in which the leaves are labeled by these permutations, pi 1, pi 2, pi n factorial. Correct? Now, what is, and the time taken for an algorithm is the maximum height of this tree. Because, I mean, you have to distinguish between all the initial, your initial data set initial set of objects might be in any of these pi i's. And at every step, you basically divide this into two parts. So if you ask this question, it divides the leaves into two parts. So you want to ask the minimum number of questions so that whatever be the pi I, you land up at the correct pi I in that many steps. So because it's a binary tree, you would require at most, you would require at least log n factorial steps. Now by Stirling's approximation, you get this is equal to order n, this is equal to omega n log n. You will require at least these many steps. Correct?
Okay, sir.
Moreover, this has been generalized to other models of computation, such as what are called algebraic model of computation, in which you basically you can at every step take some number of objects. So basically here OI is less than OJ is equivalent to asking, is F OI minus OJ greater than 0, where Fx equal to algebraic circuits. Yes, sorry, algebraic circuits. So it's asking F OI minus OJ is greater than 0, where Fx is equal to just x. Correct? So you have a polynomial and you are checking whether the value of that polynomial is greater than 0. In algebraic circuits, you can do this for some fixed degree polynomials. Correct? Here the degree, these were linear polynomial. This was a linear polynomial. You can use other polynomials, and in that case also, you can prove a similar bound of n log n. So I'm speaking from memory. I've not read this before this. This is impromptu, so it might not be 100% correct. But there's a theorem by Benor which does this. So you can look it up. Okay. More questions?
This is only the PIT, right?
Huh?
This is only the PIT, polynomial identity testing.
No, this is not polynomial identity testing. Polynomial identity testing is something very different.
Equal to 0.
Not equal to 0. Greater than 0 are the tests you are doing.
Okay, yeah.
Polynomial identity testing says that you have a polynomial and you want to know, given by a circuit, and you want to know whether that's identically 0 or not. That's a much more complicated question. Correct. So here the degree of f, I think, must be a constant. The degree of f is equal to order 1. Then an f tree requires height order n log n, omega n log n to determine the order.
Sir,
Tell me.
sorry, are we gonna like learn all this in detail later, or?
Yes. You don't have to worry about it in this thing. It's just somebody had asked, so I just, yeah.
Yes.
Okay. If not, that let me conclude today's class here, and we meet again on next Tuesday. And there's a quiz tomorrow at 11 o'clock. I will send out this thing tonight. Okay? Is that okay?
So will it include rotations and?
No, not today's this thing.
Okay.
Okay, thanks. Bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thanks.